Okay, welcome everyone to this continuation of quantum topology. Who wants to know about quantum topology? That's an excellent question. I don't know, but we'll do it anyway. So today I would like to tell you about why people care about quantum topology. Essentially. So it all boils down to, well, let's try it this way. The good old Reidemeister moves. Let's try it this way. No, not fit width, fits page. Much better. Why is this not working properly? Who knows? Much better. So the Reidemeister moves. There are usually 3 of them, and I will explain that in a second. We have them already here on screen. Yeah, if you can zoom in, here our little Reidemeister moves. Now it works. Excellent. That's pretty good. Sometimes my touch screen here has a little bit of an issue. That's what it is. We're all getting old, I guess. So the top Reidemeister moves are stolen from Wikipedia, and the bottom Reidemeister moves is how I like to think about them. And they're essentially the same, obviously, but for some reasons Wikipedia has those rectangular shaped Reidemeister moves. Anyway, so there are 3 of them, and there's a 4th unspoken one, which is essentially some type of an isotopy, an isotopy relation, which if you want to, you can think about it like something like that. Yeah, isotopy, something like that, and you would have a crossing slide along something like this equals. So you can slide it now. So you still have this thing here, but the other one slides to the other side, right? So some isotopy relations of that type that are usually going well, nobody usually points them out, but anyway. So they change the type of the diagram, you see. They don't change the type of the diagram, you see. The Reidemeister moves change the type of the diagram. That's why they're separate. Anyway, so there's type 1, type 2, type 3, and type 1 is you undo a little kink. So if you have a little string, you can just pull it straight. The other one is even more obvious. You could just separate 2 strings if one of them is on top of the other. The other takes a bit of staring, I guess, but it's actually also pretty easy. So there's this crossing here on top. Sorry, on the bottom, and this strand here goes on the top, and you really just slide this crossing through. And the interesting thing is, I haven't double checked for the Reidemeister 1 move, but you don't need any other variations of these moves, because any other variation, for example, where this string is on the bottom, will follow from the attached moves. Don't worry about the orientation here, they don't actually play a role for what I'm going to say. But in my pictures, I had just had them and I was too lazy to change it. Anyway, so there are 3 moves essentially, and those hidden isotopies. And the big theorem of Reidemeister, which I'm going to sketch how you actually could prove that. So Reidemeister, let us try to find that actually. Should have been like in the 1920s. There was a German mathematician called Kurt Reidemeister. That one. So main work, you should expect mathematicians probably have main work around when they are 30, should have been in the 30 plus or minus, right? So it's like around this age range is in the 1920s, the famous Reidemeister moves. Probably has done way more, but I have no idea. So Reidemeister moves, here you go, Reidemeister, that's where I stole those pictures from. Will you tell me from when this is actually Reidemeister? We have, there you go, 1927. We can zoom in a little bit to make it a little bit clearer. So it's kind of a nice thing. So it came up in 1927. So people were studying knots already before, and apparently they're misnamed. I didn't know that. Apparently in 1926 someone else did it independently. That happens all the time, by the way. But anyway, so they had 3 local moves, and before this really people had no idea how to study knot theory because of the following problem. I have that picture on the next slide. So knots are really 3-dimensional objects. I really love this picture. I forgot where I stole it from. It's so perfect. So knots are really these 3-dimensional objects, as you can see here. But you usually just draw their 2-dimensional shadows, but the shadow might vary a lot, right? And if you can't describe the equivalence on the shadows, you essentially have no chance to study knots. It's not quite true, but it is at least very difficult. Here's a similar picture of a knotted protein, I think. And again, you can just somehow measure with an electron microscope in this case, like a 2-dimensional shadow. So this question about how to describe two-dimensional shadows of knots is very, very important. And it turns out we are super lucky because you only have 3 moves ever. Yeah, and this funny isotopic thing. So whenever you have something like you want to describe an invariant or something, you only need to worry about 3 moves. It's pretty good, actually. It's pretty good. So it's a very important theorem, and took a while, of course, to really fly. So people tend to ignore people ignored knot theory for a while. Knot theory really become very important with Jones, because the Jones polynomial is just so good. It's just so good. But anyway, people were clearly working on knot theory for a long time, and this is kind of the main theorem, the Rademacher theorem. Kind of easy to remember. You just have 3 moves, and yeah, they're not too difficult, right? So the difficult part of the theorem is to prove that there are no other moves, because that these moves holds, that these moves are true is like trivial, almost. You can just pull out your strings and just verify that this works, or maybe you can do the mental gymnastics. So my touch screen here. Yeah. So the point is the 2 tangles are isotypic, so they're the same if their projections are related by those moves. Yeah? And you only ever have those moves. You have more complicated moves built out of those small moves. And these are the randomized moves. So really, really great. And this really reduces everything to just looking at pictures and those combinatorial equivalences. To do that in practice is not super easy. Well, there's some cost you have to pay, but you can still do it. It's not too bad. In particular, if you want an invariant, as I said, it's pretty straightforward to just, you usually just need to check 3 Rademacher moves. So if you want to discover the Jones polynomial, your paper could be very, very short. You only would need to check 3 moves, and of course discover the Jones polynomial, which is absolutely non-trivial. It is pretty easy in 26, obviously. You just ask Google or something. But 40 years ago when Jones did this, it was absolutely non-trivial. It was a really, really big breakthrough. Jones polynomial is still it's really on top of all of mathematics, essentially. It's one of the best things produced by mathematicians ever, because it's somehow this mixture of being easy and powerful somehow. Okay, and the way we describe it in quantum topology is we use algebraic models, because we like categories and algebras and that's essentially what we like. We don't like anything else. And the way I usually do this is I have this thing that I call the Brouwer category, because essentially Brouwer did this first in the 1930s. While we're doing this, there is this mathematician, Richard Brouwer. Yeah, here you go, Richard Brouwer. Yeah, and it works again. So roughly in the 1930s, you would expect whatever. Brouwer has done a lot. So in particular in finite group theory. Oops, why did I click on this? I wanted to click on that. Brouwer has done a lot, in particular in finite group theory. But it worked, for example, with Shor on various forms of representation theory. In this case, in the Brouwer category, usually describes representation of orthogonal groups. But there's this version, which I call the quantum Brouwer category. The quantum really just means we take care of crossings. And here's the relation I was trying to draw. And this is our Rademacher move. And all of the other relations are already kind of built into the quantum Brouwer category, because it's braided and pivotal. It's a very, very efficient description. It's braided and pivotal, so the Rademacher 2 and 3 moves come for free. Pivotal already implies our little zigzag friend, for example. And then some interaction relations between crossings generated by one object and those relations. And this is equivalent to tangles. Essentially, that's what it is. You could do it with orientations if you want. And that's what we like in quantum topology, right? We have algebraic models for non-algebraic objects. That's the whole point. Right? So let me, essentially you want to prove this statement. The quantum Brouwer category is equivalent to the tangles, or the oriented one is equivalent to the one with orientations, and equivalent as nice categories, as you would expect them to be equivalent. And the only difficult part is essentially to prove the Rademacher theorem, which of course you don't have to do it anymore. Rademacher did it, or as we just learned, someone else. Was one of them Alexander? Let's check. Was one of them Alexander? One of them was Alexander. Someone else did it as well, but anyway. So you don't have to prove it anymore. But roughly the proof is actually pretty brilliant. So you reduce it to the case of, well, combinatorial knots, where you just think of them as piecewise linear embeddings. Piecewise linear, so you lose a little bit, but let's just assume piecewise linear. So you have those little vertices everywhere, and then piecewise linear parts between, right? So vertex, linear, and whatever. And you define what's called a delta move or a triangle move. And triangle just means you can just push in a triangle, literally in 3 space, so there's nothing cutting through the triangle, right? That's the whole point. And then Reidemeister essentially shows that triangle equivalence is the same as what we are looking for, not equivalence. And so you only need to analyze triangle equivalence. Yeah, here's one of them. This is just a silly isotopy. You pull out the string and you shrink it again, right? Triangle equivalence. And then you have something like this. If you pull the triangle in front of another string, that's the same as doing nothing, because now the triangle is in front. You can't push it through. That's kind of the rule of the triangle. That's why I color the triangle in. It's really like a solid triangle. And this corresponds to that move. And if you want to draw now the other moves, you're happy to do that. So essentially it boils down to a few combinatorial checks of possible local moves on triangles, and you end up with a Reidemeister moves. Pretty cool way of proving it, actually. There are a lot of stupid details like, oh, why are piecewise linear knots the same as general knots? Well, they're not, but let's just assume general knots means X, and then they are. Something like that. But not super important. No, the more important is, I think, this idea of just combinatorializing the problem, which is kind of a crucial step that you hopefully eventually will learn in your life. That combinatorics is easier than essentially anything else you will ever meet. Not just in mathematics, but literally anything else. But anyway, so then we get this really beautiful quantum topology type statement that we really like, that our algebraic thing here, whatever, the category, the braided pivotal category generated by one self-dual object subject to those relations, is the same as the topological object. It's kind of the prototypical example of what quantum topology really likes to do. Right? Why is the theorem such a big deal? Oh my goodness, can I zoom in? Better. Once diagram, of course, now we can use our algebraic machine to study those knots, right? That's the whole point. And then if we play that nicely, and we hopefully do that very soon, then we get what people call quantum invariants, which is now a functor of our, let's say, a functor of our Brouwer category here, because they're equivalent, let's just use that one, into something really algebraic, like vector spaces, right? Then you associate to every topological object a very rigid algebraic object, like a vector space or a map or something like that, right? A linear map, something very easy. And then you can hopefully take something like a determinant or trace or something, and you get an invariant. That's the whole point. And it turns out that that's how it goes. Turns out that's exactly how it goes, yeah? But before we do that, we actually have this idea of imposing something a ribbon. So a ribbon is literally somehow, I don't have a really good explanation, maybe someone has, because when you do this quantum topology trick, you send the Brouwer category into something algebraic, like vector spaces. You somehow always end up with an invariant for ribbons instead of knots. What is a ribbon? A ribbon is really a thickened knot, if you want. So instead of just having one knot, like this line, now you have 2 knots that run in parallel, essentially, up to some local intersection points. And then the ribbon is literally just, you have now a surface in between. It's literally a ribbon. Like you have a belt, take your belt, and now you can twist it and knot it and whatever. That's a ribbon. It turns out that we are really describing ribbons, not knots. But anyway, but this is then, the next step is where quantum topology without topology really starts, right? We send our quantum Brouwer category, or its ribbon version, to something algebraic, and we get very, very excited and very, very happy. Or at least I get excited and very, very happy. Whether you get excited and very, very happy is very questionable. Anyway, I hope you enjoyed this video, and I also hope to see you next time.